I was an undergraduate and master's student in Canterbury in New Zealand just after World War II. Now at that time there was no books, there was no money in the university, and there were very few teachers. I think there were 3 people to teach the whole of mathematics and not much more in the physics department. And to show what it was like, at one point I went to the library to try and find a book on modern physics. I could find stuff on electromagnetism, but I wanted something more modern than that. I couldn't find anything, but I found 2 books on ether theory. Now, even I knew then that ether theory was gone, but they were interesting, and I learnt something that's been very good for me in later life, and which I like to pass on, and that is, if you were a student in the 19th century, say 1870, you better believe in ether theory, because this was the standard model, and everybody believed in it, and you only got a job if you prayed to the god of ether in the morning. And now, of course, we now know that this was all rubbish and that the university does not run in this way. Actually, I was surprised recently to hear that right up until just about 1930, there were still professors around who believed in the ether theory. So it didn't all die out. Now, I went to the university, I went straight into stage 3 mathematics from a school that didn't have a math teacher. So that quickly taught me, don't have a mentor. If you've got a mentor, you're never going to get anywhere. There wasn't much to do at Canterbury University, so after a year or so I took up billiards and other things and waited till I could get to Cambridge. When I went there, I had a good 19th century education in mathematics. This is the middle of the 20th century. But nevertheless, I did decide to do a PhD straight off, and I got the world's best algebraist as my supervisor for a while, and then I got Salam, who failed to teach me the difference between pi, mu, rho, sigma, whatever all these particles were. In those days, it was just a zoo. You had these particles that observed, and nobody had any theory as to why these, one existed and another one didn't. So then I met Salam went off to Imperial College, and I was left pretty much without a supervisor. So I was signed up with somebody called Candlin, who I never spoke to, actually. He did the sort of physics that Salam did, and by now I got interested in relativity and a particular problem. A friend of mine, John Moffat, who's at the Perimeter Institute, or was up until, he's still there, but he's retired. He had a theory to unify gravity and electromagnetism, and the theory didn't work out, but at one point he and I looked for, we took what was then called the Einstein-Infeld-Hoffmann approximation, which is now called the post-Newtonian approximation. But it was really invented in '38 by Einstein and Infeld and Hoffmann. We used that to look for the forces between the particles in his theory, and he actually got the right forces, but then we realised he didn't have enough field equations and it was all not going to work. So I noticed that Infeld and company had written a whole series of papers in which they proved they were trying to justify the post-Newtonian approximation. And each proof got worse than the previous one. I blame Infeld for this. And they all came down to them having proved that you didn't have to conserve angular momentum in general relativity. only they didn't realise they were proving that. They thought I don't know why they completely missed it. So I got very interested and I pushed this work through one level higher than anybody else had, and I looked at the fast approximation. And then I also looked at spinning particles and how they were interacting in the higher orders. This stuff died afterwards because when I got to the States I was told nobody's interested in that all this approximation stuff. So I dropped out of it. But I knew that angular momentum was important. So, where did the solution come from? Okay, this was the start. Petrov, a Russian, looked at the curvature tensor for an Einstein space. He assumed that the 10 components of the curvature, which corresponded to the Einstein equations, were 0, and that left him with the conformal tensor, which is the curvature tensor with these other components 0, and that's got 10 components. And he said, I've got this tensor and I've got the metric. Is there some sort of canonical form I can get? It's like having two matrices, you know, A plus lambda I, and looking for the eigenvalues and the eigenvectors. And he classified all possible conformal tensors. Now, we couldn't see his paper in the States at the time. This was the early 60s, because it was Kazan Institute or something, and it wasn't available where I was. So people were rushing around trying to get the same results by some other method, and I remember using projective geometry to get to it. But it's best explained in terms of spinors. It turns out there's a completely symmetric spinor that corresponds to the conformal tensor. Being completely symmetric, it's only got two indices, it's really a quartic form. It's like a fourth order polynomial in x and y, not that they're coordinates, where it's only the ratio that counts. So it's got 4 roots. So what this meant was the conformal tensor had 4 special directions that happened to be all like. Okay, now, if 2 coincided, it was called algebraically special, like a repeated root. And it turned out that Schwarzschild had 2 repeated roots. The 4 vectors, being type null, were in pairs. And the plane-fronted wave, they were all the same. So people started to wonder, gee, could we generalise, could we find all solutions of this type? And the first thing that was done was Robinson and Troutman solved the problem for when it turned out that when it was a repeated root, it was a geodesic, and it was shear free. This was, in terms of Newman-Penrose coefficients, one of them was 0. What it meant was that if you projected a rectangle onto a screen, it stayed a rectangle, it didn't skew over. Anyway, they got this metric here. Now, that was really good, because that was the best looking metric anybody had seen in years, and well, it hasn't been any use because it doesn't represent anything physically, unfortunately, which has been a great disappointment, I'm sure, but it was nice. Okay. That's been the problem with almost all solutions of the relativistic equations, that they don't represent anything physical. So now the more general problem was, in their case, they assumed that that vector, that field of geodesics, light rays, was also hypersurface orthogonal, so they lay in surfaces. Normally, a bunch of lines don't lie in a surface. Now, the more general problem, 3 groups were looking at it, Newman, Unti and Tamburino. They proved that Kerr didn't exist. They actually proved that the only possible metric in the general case was this nut metric. Robinson and Troutman chose, actually it turned out the same coordinates I chose later, because I hadn't realised that, but they chose the coordinates first, and they were calculating field equations and things. I was looking at the structure of the field equations just in general and the way the Bianchi identities worked, but I kept being told that the problem was all solved. So, I couldn't understand where it was coming from. Okay, eventually I found the paper, and this is about as deep as we'll go in the mathematics. I found this paper of theirs. I got a preprint. You know, in those days, you didn't get on the internet and look at the paper there. You had to wait for somebody to send you a physical copy, a preprint. And one was sent to the University of Texas, where I was, to Alfred Schill to check out, I suppose, for publication. And he gave it to a young friend of mine, Alan Thompson, who happened to be in the next apartment to me in an apartment building. And he looked at it, everybody agreed it was great, and he brought it in to me, and I took it, and I'm a very lazy reader, and so I went through it looking for where they proved that there wasn't anything. You know, there had to come some point where there was some big equation. And I found this equation here. It was something like 1/3 plus 2/3 minus 7/3, well actually it was minus 1/3 times a squared was 0, and the sum of these integers wasn't 0, so a squared was 0, and the whole lot fell in and Kerr didn't exist. Okay, where'd it come from? So I thumbed back and I found this equation, and I realised this was a Bianchi identity. Now, what I mean was there are identities amongst the field equations in relativity, and in particular, there will be 3 equations. If you cycle around, if you differentiate them and cycle around 3 of the indices, you get identically 0. Okay, it's not just an equation; it's an identity. So I realised it had to be 0 equals 0. Now, I then went ahead and very quickly solved the general problem and got the field equations I'll show you in a moment, which again were totally useless. But I went up and I gave, the first thing we did was I went to the guy next door, this Alan Thompson, and I said, you know, it's wrong. They made a numerical mistake. So he had to calculate one of the components. So we calculated the first one, and it was wrong, and the sum was 0. So, okay, I proceed. I go to New York and give this talk, and the guy, nobody believed it, I'm sure, because it had been proved that only the nut existed. And I was told by the person who had produced this equation that, okay, the first term may have been wrong, but so was the second. That was a misprint, so it still wasn't 0 equals 0. And I said to him, if the first 2 are wrong and it's not 0 equals 0, the third term's wrong too. So he calculated it that night, and sure enough it was wrong, and the sum was 0. But the point was, you know, you shouldn't have to calculate everything. Some things you should be able to deduce from the structure. So, okay, why did they make a mistake? I think it was because of the Newman-Penrose equations. Because what they did was they took gamma ABCs, okay, or rotation coefficients, but it's the same thing, objects with 3 indices, and they gave every component a name, alpha, beta, gamma, delta. And then they expressed all these equations in great detail. And now they've got this mishmash of the Greek letters and no way of checking whether their equation is right. And no way of knowing what the hell equation it is they're calculating. And no way of knowing that actually that's the something something 1, 2, 3, 1, 2, comma 3 plus 2, 3, comma 1 plus 3, 1, comma 2 equations, because they can't see the indices. So, in a sense, it was deserved. You can tell I'm a mean bastard. Okay, the general form, that form up there, which is a mess, got a bunch of indices, was actually the same form, I realised later, as Robinson and Troutman had. And the reason is that those are the natural coordinates for this problem. Now I went ahead and I started solving equations, and I found most of these coefficients were horrible messes. And we'll forget about all that because you don't want to know. The field equations, they were fourth derivatives, horribly nonlinear fourth derivatives of things. They weren't just del squared of something equals something. They were del to the fourth with non-linear coefficients in there, and all this. So that's the general form. They're not even consistent. Okay, so I realised I had to do something to solve these equations, because in the form I had them, I was never going to get a general solution. 50 years later, they haven't been solved. Probably doesn't matter. So what I looked at was symmetry, okay? I needed symmetry in this problem, because symmetry reduces, if the metric's independent of a coordinate, you go from partial differential equations with 3 variables, independent variables, to 2 independent variables. So I had to get rid of some of the coordinates. And here I was fortunate that I'd already looked at the general problem of finding symmetries. And what I knew was that nobody could solve the killing equations, which were usually used to calculate symmetries, especially in general metrics. They're horrible equations. There are these equations you get if you've got a symmetry. It's a vector Ka semicolon B symmetrized equals 0. They're horrible to solve. But the point is this: I knew the coordinates could be defined in this metric up to a certain group. And that's actually the group given here. The coordinate zeta was a complex coordinate, and I knew it up to an arbitrary function of zeta, an arbitrary complex function. And there were some other things I knew. So I knew what the group was, but any symmetry is an allowed coordinate transformation, because if you can transform the metric by rotating it into exactly the same form, then you can introduce coordinates there which agree with the original coordinates. So all I had to do was figure out the infinitesimal coordinate transformations from this, and that would give me all symmetries. And I did that, chug, 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 and this I'll put up on the board. But in the end, what I showed was that if it had a symmetry, I could choose the coordinates and everything, so that it was either d by dt or d by d phi. Okay, if I chose the coordinates correctly. So great. First thing I did was, suppose it's d by dt, which is what I'm talking about there. Oh, great, the equation's reduced to, gee, Pers, look at this. That's del squared of something times a del squared of something equals 0. They were horrible, horribly nonlinear. Pretty much no solutions. The problem was, to be physical, we had to be talking about a sphere-like surface. We had to have harmonic functions on it. We had to have a harmonic function on the two-sphere, unfortunately, is singular. And so, in the end, when you look at the details, you can't get non-trivial solutions of that. So, I tossed in another symmetry rotation and got to a 4-parameter solution. Okay, 4 parameters. One of them was horrible. It was not asymptotically flat, and it was singular all over the place. Second one was the nut parameter, and that's not physically interesting because it is not asymptotically flat, and the topology is just one of these mathematical curiosities. So that left me 2 parameters, which, believe it or not, were called M and A. And let's see. So I worked out what the metric looked like with that, and here was the first form. That was the first form I gave in my paper. But what I knew was that most of it, this part, which I call ds naught squared, is just Minkowski space in a strange coordinate system. So in order to see what it represented physically, I transformed it to the Kerr form, in which it's got a flat space plus the square of a null vector. So now we've got a 2-parameter asymptotically flat solution with something at the centre. What the hell is that? At this point, I told Alfred Schild, who was director of the Relativity Centre in Austin, I said, I'm going into my office to calculate the angular momentum. And Alfred said, fine, he's coming too. So we went into my room, and he sat there in an armchair smoking his pipe, and I chain smoked at my desk, and I did this calculation. Now this is the calculation. I took the metric and I expanded it at infinity. I got this in those coordinates I just had. Okay, now that's Schwarzschild there in some coordinate system. This term isn't quite a rotating solution, but because of my work on the post-Newtonian approximation, I knew that what I should get, and I knew that I should be able to get the right form with an infinitesimal coordinate transformation, and that's what an infinitesimal coordinate transformation does to the metric. This is an infinitesimal one, first order, and all I had to do was get rid of that dr term by this transformation. And clearly it was integrable, so I had no trouble. I could solve that for the AMUs, and that left me with this metric here. Okay, and that's got this term. That's the term for a rotating body with angular momentum ma at infinity. And that was known in 1920 or earlier, when people first looked at the precession of as they took a vector around a Schwarzschild solution, around any central body on a circular orbit. So anyway, so it had rotating mass, its angular momentum was ma. At this point I told Alfred Schild it's rotating, and he was extremely excited, and I wasn't quite excited because I hadn't realised how long people had been searching for this. It's truthfully. But anyway, clearly the Relativity Centre was we all knew that we had found something. Okay, other coordinate systems. Well, this was middle of 1963. Later in the year, quasars had been discovered. They'd been discovered in the 50s, but it wasn't known that they were extragalactic until, not long before this, and when it was realised that these were incredibly active galaxies out there. Where was the energy coming from? Well, the first Dallas Symposium was set up to bring everybody together to try and find a solution. And there were, I don't know, roughly 300 people, almost all astrophysicists or astronomers, and some of us relativists, at this meeting, set up by Alfred Schild and a couple of others, I might say. And I looked at the book that was published from this a few years ago, and there was no idea how you could get the energy of a quasar out of any known object. So I think Hoyle and Burbage suggested a million solar mass sun, but where was the energy coming from? It wasn't coming from nuclear energy, so didn't have a clue. I heard Roger Penrose was going to give a talk on my solution. And at this point I went to the people who were running the conference, Alpha Shield, and I said, I wasn't sitting in an audience with somebody else talking about my work, because I knew what would happen then. So I said I couldn't care less whether they understood what I was talking about or not. I was giving the talk. So I gave the talk, and there were all these astrophysicists and astronomers and relativists, and all the astrophysicists and astronomers pretty much sat there reading the paper or writing letters or something. And I gave my talk, and it showed that it had event horizons, by the way, that you could go down the axis one way, but not to come back. Anyway, I gave my talk, and at the end, Pepper Petru leapt to his feet and started shaking his fist at the audience and saying they had been working for 30 years for this, and these guys should start listening. And they basically gave him the finger, and that was that. Of course, a year or two later, I started to get the last laugh on all of this, because now, obviously, they are using this work. So that was where it came from. Fulvio Melia, whom a lot of you will know, drew me this picture of the two surfaces, which one of which is the event horizon for Kerr. If you hit the outside surface, you're going to drop through to the inner surface. You can't avoid that. What happens to a body that collapses inside that? Nobody knows. There is no interior solution to this. I believe because that's an asymptotic solution. It's not the solution for a stationary, time-independent body. And that basically it's what you get at the end of the universe. But the one thing for sure, although if you go down that axis, you can go through a singular ring which is in there, which is actually a branch. It's a branch point of a quadratic equation. You can go through there into the other half of the universe where the mass has got the opposite sign. It's negative mass instead of positive. That's nothing to do with physics, because you create this sort of an object by Sagittarius A star collapsing down. It does not open up in the centre with a ring to God only knows where, if there is a God. But so it's mathematically interesting, but that's all. But let's see. Oh, soon after this, I looked for all solutions of those algebraically special equations, which split, like the Kerr did, into flat space, Minkowski space, plus the square of a null vector. And I did this one morning, and I found that they seemed to depend upon a function of a complex variable which had to have a singularity, if it wasn't Kerr, on the unit, on the somewhere at infinity. And so I thought, that's of no physical interest, and I just threw it in the waste paper basket. I didn't even check it, but there was a party. This is going to be the end of my talk. There was a party around Christmas time of '63 for Jerry Plebanski, a Polish relativist who was living in Mexico, who was visiting in Austin. And I heard Alfred and Jerry talking at the conference, at the party, about metrics of this form, flat space plus the square of a null vector. And they didn't know of any. Hi there, are you interested? Come in. Come in. That's all right. Good girl. Anyway, I heard them talking, and I said, it's possible I know of a whole class, but I never checked it, so it might be wrong. So Alfred and I went into his office then, and we did a little calculation. We took metrics of that form, and we calculated R mu nu, K mu, K nu, the simplest field equation to calculate. And that told us that it had to be geodesic. This vector had to be geodesic. So we calculated a component of the curvature tensor, which we knew told us whether it was algebraically special, and it was. So all of a sudden at this party, with some very simple calculations, because these were the two easy things to calculate, we'd shown that if you had a metric of this type that people had looked at for on and off for a long time, it had to be algebraically special. Basically, it had to be the ones I already knew of. It turned out that was true, so that's where the Kerr metrics came from. We had to make it look a lot better because none of the stuff had been published, so we had to do everything from first principles, which made it more complicated, but it all ended up. So I thought that the trouble with them all is they've got a singularity somewhere. They are not black holes, of course, because we know that there aren't many black holes around, and so they're not physically interesting. Soon after this, I looked at what happens if you have electromagnetism in the same situation, and what I found was that you could generalize all of these metrics to charged metrics. Okay, you could, and furthermore, the electromagnetic field around them was not only a solution of the Maxwell equations in the curved space, it was a solution of the Maxwell's equations in the empty space as well. So it actually satisfies the Maxwell equations you knew and loved in your first physics courses. Okay, I think that's about time to stop. I've been talking for half an hour and the dog's left. So, she's gone to sleep. I guess the moral of this all was that it was known by me and everybody else that this was a rotating solution, and that it was, the relativists all knew that they were excited about it. Alfred Schill thought they should put at the University of Texas, it's got about a 14-story or 20-story central tower. Anyway, I remember Alfred saying that they lit up this tower with orange lights whenever the university won a football game, which is a lot of the time, because when I was there they won 33 straight football games, which is a hell of a lot. We're national champions. And he thought they should have lit it up for this metric and not for the football games. I tended to agree with him, though we both went to the football games. Okay, I'll stop there.